if we formalize this fact that friction depends on how hard the surfaces are being pushed together and the nature of the two surfaces, we get this equation. The force of friction measured in newtons is equal to mu, this coefficient of friction we call it. It's given the Greek letter mu, which kind of looks like a U with a long tail on the front end of it. Friction equals mu times the normal force. So if we increase the normal force, we get more friction. If we make two surfaces more rough with respect to each other, which would increase mu, would increase the coefficient of friction, that would increase friction. Let's go ahead and solve this equation for mu and do a quick experiment. Some books actually introduce mu this way and tell you that it's a ratio between two forces. If we divide both sides by Fn, we get mu by itself equals Ff over Fn. I'd like to try to measure mu a couple of different ways. You see I've got here a plywood track, and in order to look at mu and the coefficient of friction, we're going to slide this brick that I've covered in paper on the track. Now, we've talked about this a lot. If you've been paying attention, you know that this brick on the track is at rest. And so in the vertical direction, all the downward forces have to be offset by equal and opposite upward forces. And the downward force is the gravitational force, weight, and the upward force is what we call the normal force, the force that the surface exerts in the only direction that it can at a right angle. Okay? Now, because the weight and the normal force on flat ground are the same, I'm going to weigh this using this Newton scale. And so I'm going to hold up the scale, hold up the brick, and go ahead and weigh it. Now, I'm not sure if everything's on the screen, so I'm going to slowly lower it so you can see the weight on the scale. And each little hash mark is 2 newtons. There are 5 of them between 20 and 30. So it looks like it's on 22. So let's assume that the weight of this brick, and therefore the normal force when it's sitting on the table, is 22 newtons. Now this is a slightly different Newton scale. It only goes up to 20. But what I'm going to do is I'm going to pull this brick at a constant velocity as best I can. Now I'm pulling 4 newtons, this says, but the brick isn't moving. So if I'm pulling 4 newtons, is there a net force? And the answer is, well, no, there's not a net force because friction is pulling against me, and friction is able to be 4 newtons. But if I pull a little harder, okay, now it reads about 7 newtons, 7 newtons, 7 newtons. I'm pulling it at a constant velocity, which means it's not accelerating. So if I'm pulling 7 newtons and it's not accelerating, we can deduce that friction is also pulling 7 newtons the other way. So we can put this in our equation, and we have friction pulling 7 newtons, and the normal force was the weight, 22 newtons. And when we divide 7 by 22, 7 divided by 22 is 0.32. So we get a coefficient of friction of 0.32. Now friction often varies between a very small number like 0.1, 0.05, that's very little friction, and sometimes as much as 4. Like good tires on dry pavement have a coefficient probably close to 4. Okay, so let's do something different. Let's flip the brick onto its bottom and see if that changes anything. The reason we're going to flip the brick onto its other side is because there's sandpaper. We were dragging it paper on plywood. This is 200 grit sandpaper. Let's see how that changes things. Again, I am going to pull the brick at a constant velocity. Again, why at a constant velocity? Because if it's moving at a constant velocity, it's not accelerating, which means the net force on it has to be 0. F net equals ma. If A is 0, F net is 0. And by that, we can deduce that friction must be the same as how hard I'm pulling. I know that's hard to see, but it oscillated between 15 and 16, really. 15 and a half. Whoops, I hit the C-clamp. Let's call it 15. It is close to 15 and a half. So this was mu paper, and this is mu sandpaper. Mu is the friction force divided by the normal force. The friction force, though, was 15 now, and the normal force was the same 22 Newton brick weight that we had before. 15 divided by 22 is 0.68. So look at that. 0.68 is more than double 0.32. So by using a different surface, sandpaper in this case on plywood, we had a coefficient that was double what the coefficient was when it was just paper on plywood. So I'm hoping you get a sense of what mu is. Mu is a measure of how much friction there really is between two surfaces, and that of course also depends, and the ultimate force I had to pull depends on two things. The normal force, Fn, how hard they were being pushed together, and the nature of the surfaces, which is what we changed, the mu.